how would you describe your job? What is I think your email signature said a sales engineer. Is that?
Yeah, sales engineer, I would say, that it reflects it pretty well. National account executive, I think is my latest title, technically. But yeah, I think sales engineer, it's kind of that where kind of a technical degree and a sales role, kind of technical sales, is probably where I'd put it best, right? Or where I self-identify. Because yeah, by schooling, yeah, I didn't school sales by schooling. No, I did not learn that. I did not know I was going to go down this path. Schooling was very much in engineering. So it was, yeah, very science and math based, for sure.
What kind
But
of degree do you have?
well, yeah, so I have a mechanical degree, out of, University of Akron. So the Zips. And, and so that's where, kind of right out of school got into the combustion field. And then over time, especially this role is much more controls based. So not that I'm an electrical engineer, but it's more of I have an appreciation for electrical, is, my role today.
And I know it's been a while, but can you remember in high school, since college is the hot topic, can you remember in high school, was there ever a point in time where you knew that you were just going to go to college because that's what you're doing? Or was it like a decision that you actually made?
Um, I would say I knew. And in my case, I'm the youngest of five brothers. So that, as you got to know me, that kind of were makes sense of me. Um, you know, And so yeah, and my four older brothers, a few of them were pretty similar, right? And so I saw a path of 2 years ahead of me, and we're every other year too, 2 years, 4 years, 6 years, 8 years. So I could envision a couple different paths. And some of my older brothers, two of the oldest, were mechanical engineers. One even went to the same school, University of Akron. The other one went to the University of Dayton, in Ohio. So it was just conversations, and the environment that I was in was, wait, we got skills for this. My older brothers could see something in me. And I'm like, I really didn't know. I mean, as a 17, 18-year old, those hard decisions that you have to make, I basically put, kind of trust in my circles of, well, wait, they recommended it. And I'm like, okay, let's give this a shot, right? What other posture can you have as a 17 or 18-year-old? Or at least where I was. So yeah, so that was more of uh, that was a really good decision, recommendation by my brothers.
What'd you get into after school? Because mechanical engineering is a very broad degree. How'd you eventually get into combustion?
Yeah. Oh, good question. I think the immediate pivot point was, okay, so I um, got this degree, and I would say my senior project was in radiators, for our school team. And it was in the radiator design. So it was, I mean, heating and cooling, sometimes, opposites of each other a little bit. Um, and that's where I think from a trade show, there's a strong, burner manufacturer presence in Northeast Ohio. There's a couple out there. And one of them, was like, hey, I was interested, and they're like, hey, we do burners and fire. And as a recent graduate, uh, I mean, I had, thermal control systems, TCS, maybe is that what we called it? So it was very much of the components, but, at that time, I still couldn't see the whole picture, of what a system like this would look like. But I think I had enough of a background where that burner manufacturer was saying, all right, they were kind of willing to pick me up of, let's tell you about the combustion. Other than that, it was, um, a little bit of class that kind of touched on that subject, or, my internships were elsewhere. My internship was in tires. I thought I was going to be a tire engineer at Bridgestone Firestone until 2008 happened, right? So they kind of got rid of their co-op program. And then I experimented in, a completely different field, orthopedics, orthopedic out of Warsaw, Indiana. That's kind of like the heart of orthopedics in the country. There's several manufacturers there. And that's where I really started to learn of, Well, wait. This isn't quite a miraculous process. It is super simple of drills, hammers, and metal fixtures. But there's the miracle part of it is how fascinating the engineering versus what the body can do. So that really opened my eyes. So yeah, so my two backgrounds of co-ops or internships, whatever you want to call it, um, graduating, like, wait, I didn't take either of those paths. So combustion was a whole new path. And boy, I'm glad I did because now I think I could put it simply. I love fire. It is fascinating. It is wonderful. It is powerful. It is symbolic. Um, yeah, I just kind of decade in, um, is kind of where I've settled.
So you are now with SCC. Can you describe what SCC is and its relations to Siemens as a global company? Because I think a lot of people get confused on the role of SCC.
Yeah, great question. So yes, so our legal company name is SCC, right? So we'll think of it for this conversation as just three letters, right? And from a historical perspective, the components, it was very few components, you know, decades ago, was the these components used to be out of Siemens Buffalo Grove or Building Technologies. That Building Technologies is one of the 9 divisions of Siemens, I believe, like Siemens Energy, I think Siemens Medical, Siemens Industry, et cetera, et cetera. Because Siemens is a great company. And so the case was made by our president, who's still with SCC today, to say, and I'm going to put it simply, right, that, wait, hey, it kind of a spin-off company of a separate autonomous company outside of, say, Siemens Building Technologies, which, has a lot of employees and stocking and all that fun stuff kind of tied into a bigger portion where if you break that out, kind of a separate autonomous company, then you could be more nimble and there was a growth plan there. And that idea was presented. And then that idea simply was granted. So that was, we'll say, the birth of what SCC is now. At that point, it wasn't SCC. It changed a couple names. But in terms of the concept of who we are today, does come from Siemens Building Technologies. And then we're a separate autonomous company. However, we are still very much tied to Siemens, the manufacturing of the combustion components, because there is a contract of SCC sells the combustion components, especially today, because the portfolio has gotten bigger and bigger over the years, for North and South America. So it was more of these components come in. We're essentially the face of the manufacturer. Like there's not necessarily a second alternative for North America and South America. So we're kind of a combination of, are we a manufacturer? And we do manufacture things, yes. Um, as well as a sales office, I would say yes, we are both of those things. Um, but in terms of, I would say, the Siemens combustion products, where, hey, if we essentially are the manufacturer, yeah, from a tech support, from a stocking, um, from all that, because we wouldn't recommend, hey, Mr. Customer, talk to somebody in Germany. We wouldn't want to do that. We'd say, well, wait, no, we'll handle that. We'll handle their inquiry. We'll take care of you. Um, and then, and then it's more of there's a relationship between the factory, which is in Germany, and Siemens, and ourselves. There's plenty of dialogue and connections there.
So that's a good difference in understanding that while Siemens may be connected at the top, the SCC is much different. And I've seen people and heard of people calling their local Siemens Building Technologies, like controls company, local field office, and asking for combustion support, and they're like, we have no idea what you're talking about. That's not us. And
Correct. Yep. And that's where, and it's hard because as there's so many divisions of Siemens, and just like our group, we get asked for, hey, what about the Siemens widget, XYZ, and I say, oh, that's not our group, and I'll try to point them in the right direction. Um, I guess that's one of the downsides of a great big company. Of We're a great big company, we're not all in one spot. But if we're all in one spot, that would be really hard to manage and run. Where kind of that model of I'm going to use a term, this is for me, kind of that decentralized command where, well, wait, if you could be a little more nimble and agile in small to medium sized companies, that there's maybe some fruit there, but I realize there's a lot of strategy, that goes into that. And the other thing worth mentioning, that really helps folks is if you go to, say, something like Siemens.com, you're going to get all sorts of stuff, right? But if you go to scccombustion.com, you'll find a website specifically on the combustion stuff, much easier to handle. So I like to throw that out there. Sometimes the website is a good indicator of, wait, go to our website. This is our scope. This is ours, to try to understand that better.
Yep. So basically, SCC, while connected to Siemens, is its own corporate entity. And if you have combustion issues or whatever, and you need to talk about components or anything, you go to scccombustion.com or you call them. I would say they have the unofficial number one rated customer service of any combustion company. You call them, you email them, they're normally getting back to you within the hour, and their technical support people are great. I've only heard great things about SEC support for their products, and they will, even on troublesome calls, they may even fly people out to help you. So that is something that is very, very rare today as far as manufacturing and support, especially when so many companies are offshoring support, or now I guess it's trendy to say, hey, just talk to our AI chatbot support. But
Oh man,
we're I don't think the combustion field is ready for AI chatbot support because it's really just product level support. But if you're, hopefully when you're calling technical support, you are calling because you have a specific issue and there's tons of variables. And while you may have not seen it, SCC probably sees it all the time, and they'll be able to help you with that. But that's my little plug for SCC support. You should always contact them. Their support line and email is excellent.
I appreciate that. I mean, because that's where, from as SEC, we try to share some of those same messages, but I think it's really easy for a company to say, wait, we're world class customer support. I mean, it's one of the bullet points in every company. But to hear it from someone like yourself, that we want to be known for that and have that reputation, I really appreciate that, Eric.
So a lot of people know SCC for their, on the boiler side, the burner products for that get attached to boilers, LMV3, LMV5, and you are on the process burner side. Can you talk a little bit more about that?
Yes. Yep. So we do have, in terms of sales teams, we do have, we'll say, two sets of groups of, one group is specifically for boilers, and the other group is everything else. Process is one word, industrial market. We've called it that way. And so, yeah, so that everything else is, ovens, dryers, furnaces, um, and those are very encompassing terms, and there's clearly more specific applications, if you really want to chisel that down. Um, so yeah, it's, that everything else is what, I'm a part of, and I'm a leader of our industrial team, on this sales side.
What, for the people who don't know, what kind of products, like goals or products or manufacturing types? So when you say ovens and furnaces, people probably think of their kitchen oven or the furnace in their house, but we're talking about industrial sized ovens and furnaces. Like what are we using? What are we manufacturing, or the process? Just some quick examples of what an oven or furnace would be in an industrial application.
Yes. So great question. And actually, I think about this type of question because even in the combustion field, and maybe you get a little bit of this too, Eric, of describing what we do because it's that behind the scenes, you know, and I mean like loved ones at a broad party, right? It's like, wait, they don't really know, stoichiometric and things like that. So yeah, I'd very much appreciate this question. So one of them, right, something common like laundry dryers, for example. Laundry dryers, there's the one in our home. Like, okay, you hit the button, there's heat, there's fuel in there, there's a little fire, it heats up gas or electric, of a laundry dryer. But then it's more of a, okay, so in great big, let's say Vegas hotels that has a massive laundry load, it's very practical for them to have a laundry dryer 10 feet tall, right? With say an 8-foot drum, right? That gets all these linens and towels and what have you. And in that case, you need, oh, I don't know, maybe 3 million BTU per hour, right? So quite a bit, quite a large burner, right? So that's where, okay, something small that's in our house that we all know of, that's, real small flame in there, to imagine that being bigger, and on an industrial scale, with quite a large flame, a lot of heat. Yeah, laundry dryer is one example. Cereal, love cereal, Kellogg's, Rice Krispies, any of that fun stuff. There are some really unique industrial processes, and at some point, yeah, it does need to go through an oven, whether it's roasted, whether it's dried, whether it's baked. Um, um, at, from my standpoint, I mean, all those applications, I'm a time and temperature, right? What temperature do you want? And then our controls, kind of controls that temperature. But yeah, there's all sorts of nuances of, wait, how does the Rice Krispie get to what it looks like? And heat is definitely a part of that process. Um, and then something like, to explain furnaces or like metals, anything metal, it doesn't come from the raw earth like that. So that raw material coming from the earth needs to get processed and handled, and heat is definitely a part of that. And this is where we get very high temperatures, 1,800 degrees, 2,000 degrees, almost 3,000 degrees, um, where it's kind of hard to imagine something that hot. But the best that I can say is, glowing refractory at 2,100, 2,200, 2,500 degrees Fahrenheit, kind of looks like the sun. You're going to want to be several yards away. If a big furnace, that hot starts to open up, which I reference that because I've seen that before, which is very interesting. So yeah, so temperatures need to get that hot to make steel, to melt metals, uh, to forge and heat treat and all these really unique specialized processes. That heat is a critical component, of forming something like metals.
Yeah, looping
So
this in back with boilers, all boiler manufacturers will have a heat treat furnace. I'm forgetting the proper term right now, but they put the boiler vessel, they weld it all up, they put the boiler vessel in, and then it heats it all up to a certain temperature, and then it slowly cools it. And that would be a example of a large uh, furnace or oven kind of process of, hey, how do I heat up a boiler that's 20 foot long? Well, you got to have this big room with big doors that are insulated. You slide this boiler in, you heat it up, and I guess something about the metal crystallization in the welds.
there, yep,
Yeah,
yeah,
something. I'm forgetting the process name right now, but
yeah.
uh, then it slowly cools, and now the boiler is good to go. But a lot of people don't know that that actually happens. Yeah, any food that is made at a commercial scale is going to be done with large ovens. Think about if you had to bake, you bake 12 Rice Krispie treats in your, kitchen. Well, now you got to bake 12,000 every hour. How are you going to do that? Well, you just need some giant furnaces and ovens to do that. And so how do we get the heat into those ovens? Is it a bunch of little burners? Like what are the kind of differences of burners and burner styles that you would see typically on an oven? Because a lot of people think of like a gun type burner on the front of a boiler, Where are some different oven and furnace burners?
Yeah. So yeah, so I'd say the gun style, I'll call it package burner, right? Where here comes a blower, right? And for combustion, you need three things. You need oxygen, fuel, and a source of ignition, right? So built-in blower, oxygen and air. That's real simple. And then here comes the fuel. So yeah, so kind of that nozzle mix package burner, gun style burner, very popular. It's very practical for, say, a single burner application. Now, if you got multiple burners, particularly on a furnace, a high temperature furnace is certainly going to have a lot of burners on it. You can imagine three, four burners, high and low type arrangement. Um, because you don't want the flames to kind of impinge on each other. Um, and in that case, it's like, well, wait, let's do one large blower, and then let's connect all the air. Let's manifold it, right, and then separate it down. That makes a lot of practical sense. Um, and that's still a nozzle mix burner, but that's basically a nozzle mix burner less the blower. Another really popular burner is a raw gas burner. And since we've got the advantage of video here, it's like a V-shaped burner, right? So if you can imagine, kind of like very simply kind of a pipe with holes in it, and then the kind of these shields, these aeration plates, with holes in them, so you can see, and then there's process air behind say the V burner, and then the holes are very strategic because the amount of holes in the plate is the amount of air that goes through, that really it gets to the flame for a good, stable combustion. That is a very common dryer process fan. I want to take makeup air market. I want to take ambient air, and I want to heat it up to, 70 degrees for a comfortable room. Direct fired raw gas burner, that V-shaped burner. And that's what's cool is those V-shaped burners, they're kind of in linear feet. So there's kind of an unofficial, million BTU per foot. So if you got a real big duct, you can get a real long burner to get more BTUs. Or you can get really fun shapes, as in like the H shape, as in a profile, in a duct, or an X or a T. Um, there's different advantages there for a raw gas burner. Um, yeah, then there's some specialty versions of low NOx. And low NOx, you really care about really the mixing, right? Because a hot concentrated flame is what creates NOx. So you want to dissipate the flame somehow. And that's either by air staging or fuel staging, or you can add excess air to cool down the flame, and a cooler flame makes less NOx. So there's a few, we're getting really specialized, right? We started broad. I think we're getting more and more specialized, but yeah, that's certainly where that conversation could go. But
Do you also
yeah.
do controls for like the strip burners or infrared? I'm thinking like the long row.
We do some of that. That's not a big thing that we do. Yeah, I think I would say that's a very specialized case.
Okay.
In our case.
What what kind of control? So you have multiple burners on a oven, and by oven, think of like the size of your house oven. Um, what kind of how do you control the air and fuel for all those burners so that they talk to each other and then talk to the other components of the oven so that the piece or part or whatever is passing through at the proper time and temperature?
Yeah. So I would say, we'll start with simple. I'd say the simplest controls are constant air and simply just, modulating fuel. Because a lot of these, I would put a category, high velocity nozzle mix burners. They're designed for really high excess air. And when I say really high, from a percentage standpoint, 5,000, 6,000% excess air, right? So essentially, you can take full high fire air, so full air, and modulate all the way down, say 40 to 1, 50 to 1, from stoichiometric, right? So here's air, here's fuel, all the way down where that flame is down to like your fist or even a big candle. That's how small that flame can get with that much excess air. So yeah, so I would say that's probably the simplest where, and then it's just, hey, putting a butterfly valve on fuel. You want more fuel, more heat. Okay. Connect it to a temperature controller and off you go. If you want to control to a certain temperature, the fuel valve then responds to that. Super simple. I would say, but the biggest downside of constant air and modulating fuel is inefficiency, right? There's all that extra air, right? So if you're heating something to 400, 500 degrees, all that extra air also it has to get heated to 400, 500 degrees, which is essentially waste. So if you can, that's where the next control scheme I'll say is ratio regulator, right? Where you can use a pneumatic cross-connected, where you take basically an air pressure and put it to the air side of a diaphragm on a ratio regulator, um, and then you modulate the air, and then as the air flow goes down, and then as the disc closes, the pressure downstream of the butterfly valve also goes down, and then that air impulsing pressure goes to the ratio regulator, and the job of the ratio regulator is to have the air pressure match the gas pressure. So you would modulate air, and then the gas pressure would follow right in line, all pneumatically, with a cross-connected uh, ratio regulator. And the benefit of that is you get rid of now instead of just modulating fuel, you're modulating air. So you're getting rid of all that excess air, that we'll say waste air, you could call it. If you want, we say 400, 500 degrees, and you're running on stoichiometric ratio. So for efficiency purposes, ratio regulator is a really practical tool. And then I would say the third step is what I would call parallel positioning. So, and this is where a lot of what our LMV3 and LMV5 systems come in. And actually, this is a good bridge because the automotive market years ago, let's say mid 1980s or so, transitioned from carburetor to direct fuel injection, right? And then all cars today are direct fuel injection, right? And so, and I'm starting to learn some of the history of this. I'd like to learn more. But one of the big reasons for the transition from carburetor to direct fuel injection was horsepower. If you independently control air and fuel, which is what direct fuel injection is, you can get more horsepower out of your car. You could also get more fuel efficiency. You could also get better emissions, right? Because gasoline and cars is a huge emission emitter. So limiting that and having regulations and controls of, hey, let's do direct fuel injection to optimize this car performance. Where let's connect it to kind of this third control method of first was full excess air. Second control method was ratio regulator. And the third method is parallel positioning, is putting, say, an actuator on the fuel, an actuator on the air, and electronically air fuel ratio, where you could tell those actuators where to go based off of firing rate. So I would almost connect the parallel positioning and the combustion field to use the analogy of direct fuel injection of what cars have done. And this is interesting. I've heard a line internally, but it's hard to prove this per se, but in general, the combustion industry is about a decade, or you can even argue even longer than a decade in terms of technology behind that. The combustion industry is about a decade behind the automotive market, of about 10 years or so. Have you heard that analogy? I don't know if, or have you recognized that now that I've said it?
I would
What do you think?
say 10 years is being easy on the combustion industry.
Okay. Yeah.
So I'm on LinkedIn all the time, and
Yeah.
if you're posting on LinkedIn and like showing like what you're doing, and if you thought the market was what's showing up on LinkedIn, basically those are the leading companies or the company that are putting themselves out there. And they're normally very specialized in the burner or boiler market, and they're always upgrading controls. Well, I have, and they're like, oh, we've been doing parallel positioning since, when it first came out, and we're constantly upgrading burners and, upgrading parallel positioning systems. And there are giant markets in the United States geographically, and there are companies out there that have not even touched parallel positioning, even though it's been out for 10 plus years, easy. I know a company that just installed a LMV5 on a burner for the first time last year, and that was their first experience with parallel positioning. And it's like, okay, that's at the time 2024. In 2024, this is your first experience, yet you talk to other people and they're not, as mindful of the geography of the United States. They're like, oh, everybody has parallel positioning. If you have linkage, just rip it off. If it's manual control, just rip it off. Everybody has parallel positioning. Everybody understands that. It's like, well, no, like the I guess every industry, but combustion especially, and manufacturers, they're very resistant to change, because if it works, why change it? And when you're starting to put on a new control system and your local rep or somebody doesn't fully support or understand the control system, because I think the biggest problem with parallel positioning is we have this mindset of, we have these general mechanical contractors, and hey, we work on everything HVAC. If it heats or cools, we work on it. And you can't learn the LMV5, LMV3, or any other parallel positioning system if you work on it twice a year and you randomly come across it. But if you can learn linkage and get by with linkage, because that's what people did for 30 or 40 years when they were in HVAC. But now every single manufacturer has their own control system and menus and all this stuff. And the diagnostics are way easier. Everything's way easier. Parallel positioning is 100% better than linkage. But you have to understand it and have people support it. And the training of that is training and adoption of electronic control system is not as widespread as people on the internet will have you believe. And there's still tons of people who prefer good old linkage mechanical control because they just don't understand parallel positioning. And I would say most manufacturers dropped down equipment in 1960 and never looked at it again. It's been serviced, it's been running, and they just patch it along, and there's an inch of dust and whatever garbage all over the equipment. Nobody can read any of the tags anymore. And now it's 2025 and 2 generations have passed. Nobody knows what's going on with the equipment. They barely have any wiring diagrams, piping diagrams, but it's just worked. But now they're looking at this like capital cost of, do we replace this? What do we do? The manufacturer isn't available anymore, like all this stuff. And it's like, well, who understands this stuff enough that to make decisions and say, yes, to spend $3 million to replace this oven or whatever it is, this is what you need to do. And that's a very specialized decision, and it's a huge capital cost. And I'm sure you can speak more on this. Whereas, oh, we just have this 1960s oven that's, yeah, it's not great. Yeah, they tell us it's inefficient, but it works.
Correct.
So I would say 20 plus years easy. I mean, I've talked to people who had boilers from 1960, 1970, and they're like, what's wrong with it? It still makes steam. I'm like, do you see this electrical panel? Having somebody troubleshoot this boiler for 3 hours to try to understand the issue is not normal. You should be able to walk in, get a diagnostic, and go right to the problem. This is not normal. Yeah, I mean, that's how the industry is, but it comes to education and awareness. And yes, you can definitely speak to more to this of like the adoption process of the LMV3 and 5 on boilers. While it seems super simple, just human On paper it makes sense. The maths out, but human nature is not as simple as math and logic. I would assume the process market is even slower to adapt because of larger projects, more on the line. You know, if our oven and furnace goes down because we just tried to convert to a new control system and the integration wasn't perfect, now the plant manager's like, what's going on? We're not making product, and they want it fixed. And yeah,
And that's the number one thing they care about, because if it influences a product, then it's like, wait, those are more challenging conversations. um and that's why, and maybe your encouragement as we're talking about this, I wonder how the market in general, right? Because this is a lot of car manufacturers, a lot of personnel, drivers, general population, mechanics as well, right? Well, that's a critical part to this. That when the transition happened from carburetors to direct fuel injections, it's and it happened, I feel like, fairly fast. I don't know, in a decade or so, because I think, 1985, I think, was the first mass-produced direct fuel injection car. And easy on the don't heart me on the specifics, but ish, right, mid '80s. And then shoot, I know when I got my first car in 1990, it was a 1995 car. It was an older car at the time that definitely had direct fuel injection. So I would say how direct fuel injection transitioned, particularly on mechanics, on manufacturers. That's the history I think I want to understand. And because I do see that's where things are happening on the boiler side as well as the industrial side. Parallel positioning is trending up. And as, say, the manufacturer or the sales of LMV3 and LMV5, those are parallel positioning systems. We're definitely seeing a trend, very much in the industrial side, a significant trend, of going up. And but I would say, in terms of a curve, it's just starting. It's kind of just starting. Uh, it's it's not like in the thousands or at scale. I would say we're not there yet, but it seems to be trending there because the incentives are all there. The better efficiency, the better emissions, the elevated light off, that flexibility of it. Hey, starts every time, burner, car, that analogy. And, um, and, and yeah, and that's where, as a manufacturer, we recognize that if the general market, as the general market gets more comfortable with parallel positioning, that's good for the whole market. Right. In terms of efficiency, that's good for everybody. Because we also do fuel only control. We also do ratio regulator. We also do parallel positioning. But it's more of well, wait, hold on a second. This best controls, is the most fuel efficient, does get more burner performance. You could do a lot more with parallel positioning, than you can with, say, the other simpler controls. So yeah. And actually, that's the room I'm in here today, is actually our training room, which is why we're all about training. Actually, during COVID, maybe I think you'll appreciate this, that we did our full training. We put it all on YouTube. So as a manufacturer, it's like, wait, training, could it be a revenue generator? Not really. It's not intended for that. It's very much rooted in, we want to make it affordable, to learn, and we support, that learning in any way that we can, at scale. Um, so
yeah,
yeah, hopefully
that's
you'll appreciate some of those initiatives.
the training from on the manufacturer side. As somebody who's sells training, the training for manufacturers, for them charging for it, the more barriers of entry you put in front of your product. And a lot of manufacturers, not necessarily in combustion, but there are in combustion, but even outside, like there's a green tractor manufacturer that puts all these controls, and hey, you can't get this software, you can't get this. Well, we're not going to teach you this because you're not an authorized dealer and all this stuff. And when you put all those things in, yes, you can make the uh, corporate math work out to, hey, we want to control our product and control is better, and because we want it to the highest standards and all this stuff. Yes, but that doesn't help somebody that is trying to fix their product at 9 p.m. on a Friday, and they can't get anybody out from the authorized manufacturer representative for 3 weeks. And if they can go look up how to use your product, and your software is free online and they can download it and they can understand your product, and there's no limits or subscriptions or just these artificial walls that manufacturers put up just to try to maintain more control or to eke out that extra dollar of profit. Now people are like, well, this is the system I want to buy because I'm not locked into, oh, I only can call this one service company, and they know that they're the only company that I can call. So now they're going to screw me over on parts and service. And I found that their service isn't even great, even though that they're supposed to be the experts. They don't know everything. So I feel like I want to go like this route. And basically all manufacturing is basically the same in 2025. There's no engineers move between companies, and yeah, people may excel in a little here, a little there, but where it really comes in is product support, which SCC does very well, product support and training. And if you can't train people on your product and nobody knows how to use it and you can't get support for it, your product is useless. And it could be the coolest product ever and save the company amazing amounts of money. But if once it stops working, if nobody knows how to work on it, might as well throw it in the garbage. And
Yep.
I think, and that's what a lot of companies, especially on the executive, corporate level, have to get in their mind of. It's for a boiler to run that's especially attached to a process, or for a burner to run, the initial cost and all that stuff, it really doesn't matter. It's, can I get support, and will it work when we need it to work? And that, getting somebody to tell you, yes, it's going to work when it needs to work, and actually stand behind that, is very, very difficult in 2025. Because just as a whole industry, and this is everybody in the technical field, there are less and less experienced people out there, such as yourself, and there are people retiring every single day and every single year, and we see the trends, and you're not always going to be able to call and have somebody with 30 years experience come out to your facility and say, oh yeah, this oven from 1970, yeah, let me work on it. You're going to have to start making amends and dealing with it, and not putting off training and just expecting people to understand new complicated products just because you installed it and paid $2 million to install it. It doesn't, the math doesn't work out when you have to install the product, and then why did you just pay all that money and then you're not paying for training and all that stuff? I see it on the boiler side a ton. I mean, process burners as well, of just nobody wants to pay for training. It seems everybody wants that 5-year experience, but it's how do we get people to that 5 years experience? Somebody has to put out the money, and yes, there is personal responsibility side of it. I think about this all the time, but
Yeah.
there's so many companies out there that just expect, 20 years experience is always going to be showing up in that van whenever we call. And that is unrealistic, and it can't happen unless you want to pay for the single person. But now I've seen so many times manufacturers rely on one single person from another company to know their process. Every time it goes down, we're calling that person, and only they know how to fix this process. Well, now you just put your entire process in the hands of one person. It's like, well, how about we pay for training for some other people? Oh no, we don't have time for that. And so product support, very, very important. And
Yes.
SCC, once again, very, very good at it. So how do manufacturers, or what on the oven side, on the end user, what problems are they dealing with where an LMV3 or parallel positioning or SCC products can help? What would somebody, why would somebody upgrade versus of, just it pencils out math wise of, hey, you can save money because you're now using less fuel and electricity.
Yep. So there's that incentive. There's the, I would say the start every time incentive, because parallel positioning, not only do you have your modulation range, but you can light anywhere you want. Right. And so yes, so if you're traditionally you light at low fire or idle condition, where it's like, wait, that's not the best performance to light. How about 30, 35, percent firing rate, or, 20 degrees, something like that. Wait, give it a little bit more gas and air, get good mixing. So that way, instead of lighting, say 95% of the time, it lights 99, get that improvement. I think that's kind of an underrated aspect. Also turn down, you can get, because you got independent, say air and fuel control. And let's say you got your oven where you got one product, and I'm just going to make up some numbers here, that, oh, you need that oven to go to 800 degrees. But you also got, you got a dry out product where, wait, I want to control down to 200 degrees. Where it's like, wait a second, that's from a temperature range, that's quite a bit of range. So to utilize that burner turn down, and one way to accomplish that is maybe, by adding a whole bunch of excess air, which you could do that. Or it's, wait, let's at least, let's add some excess air at low fire. But we can optimize that a little bit better, and we can find that spot where if the burner doesn't like, a certain air fuel ratio, then, we can try a different one, because we have, in terms of degrees of freedom, we can adjust the air up or down, and we can adjust the fuel up or down at any given point. So we have a lot of different levers that we could try to find sweet spots of burners, improve reliability, and just overall burner performance, is that. So that having that wide temperature range is critical, for some applications. The other thing is the troubleshooting, and I think you alluded to this a little bit, because it's electronic. I'm going to be real loose with the term. I would say smart, but it knows a lot more than, say, a traditional mechanical system. Right? Where if you can walk in and say, wait, I get an error message that tells me in plain text, or I get a diagnostic code and I know where that information is. Those diagnostic codes, those are really good. That is unbiased, great information of what the control unit is trying to tell the operator, to say, this is the reason why I faulted. And that communication, is critical, because then it's more of a, wait, some red light is on, here's alarm, what's going on, why is it yelling at me? Okay, air pressure switch, bang, focus on the air pressure switch, either it's failed or whatever, get a new air pressure switch, off we go, here we go, we're up and running, rather than trying to chase limit strings or getting your voltmeter. That electronic aspect of it has, a lot more visibility, which, as service technicians, get more comfortable with, say, the diagnostic codes and the troubleshooting, then everybody wins in that case. The manufacturer, the end user, if they are down, they can get up quickly, because the diagnostic was very specific from the service technician side or the operator, that, if they're more comfortable with it, like, I know how the system works. Voila, I know it's air pressure switch. Let me replace that. Hopefully they got a spare, swap out a couple wires, and it's a very quick change. And now you're making whatever widget, that you were before. So that's where some of the benefits of, that electronic type system, and I'm particularly contrasting it with that mechanical, of whether it's a linkage or a ratio regulator is a mechanical device, kind of contrasting that with those more traditional solutions.
I would also say, and you can correct me if I'm wrong, that it's a tried and true logic process. So instead of somebody coming in, and I've seen this on the building control side, as specifying engineer says, we want our controls manufacturer to write the control sequences of all the equipment because we want complete custom control. But it's like, well, who knows a boiler the best or a control system best? It's the manufacturer. So like a boiler plant supervisory control system from a manufacturer already has all the control sequences in there and you just change the settings. With an LMV5 or LMV3 parallel positioning system, all the controls and processes are in there for a safe burner, and you're not letting somebody else try to program and sequence all those things. And it's already tried and true, and it's a packaged unit, and you just wire it up how the manual says. And there's all different variations. It's not, oh, it only works this one way. There's all kinds of different selections on the inputs, outputs that you can do and how you want to run your burner. But it's a tried and true logic where it's packaged, and you're not relying on an expert. That I've seen it where somebody comes in and programs a custom PLC to run a burner. Well, that person retires or moves on to a different company, and now nobody knows how that custom PLC works, and somebody has to come back and figure out what the old person did. And sometimes you just don't need that level of complication where you can, if you just have a packaged control system where an LMV5 is just packaged and it works, and it's the same product from with multiple locations. If you have a manufacturer with 10 locations, you can buy 10 LMV5s and have the same exact product across all of them in all the same settings. And you're not relying on, your 55-year-old custom coder to build you a PLC system and write code and do all this stuff and to try to understand it if you don't need that stuff. Is that correct?
Absolutely. And actually, just to put language to it, I would say it's the discussion, and it's a bit nuanced here, the difference between programmable versus configurable. So by implication, a programmable kind of implies that it needs a programmer. And that's your 55-year-old, done it a long time, controls engineer, where configurable is more of a, I have some flexibility in this system, but it's more of a 0 or 1 or on or off or this flavor or that flavor. And so configurable is, from a liability standpoint, is proven, tested, field. You just stay in those configurations and you're good to go, particularly on the program sequence, like the shutoff valves and the interlocks, all that which is critical safety stuff. The LMV systems, I would say, are very configurable, right? They're prepackaged, engineered, and you just got to be like, oh, I just want this version, this version, this version. Okay. And then off you go. Where programmable kind of implies, okay, let's truly program it from a code or line by line or starting from scratch. Where that's, that means there's a lot of liability on that programmer. And they've been doing it for a long time. I'm sure they could do it safely. Absolutely. But then also as a business risk, I don't know if that's a risk you want to take, of say a programmable system, say like a PLC system, because some of this stuff can all be done in a PLC, versus an LMV where it's pre-engineered, it's approved, it's the standards, and it's all streamlined at scale, rather than say one system where kind of a custom program. So yeah, I would say that's a great value. As well as a maintenance standpoint, because it's a universal system, right? If you call us, the same LMV3 is the same LMV3, right? As well as liability, where, hey, Lord willing, if something were to happen, that you're relying on something that's been field tested, and proven.
How would
So
a manufacturer or representative or somebody who's consulting an end user, how would they, because I always think about, rise to the level of complexion that's needed. So how would they determine that an LMV5 can work for their process versus, hey, we need a full-blown custom PLC because this is so specialized that it can't work? What was that process? Who would determine that?
that's a good one. I would say there's not necessarily a known line. I think it probably starts with the programmer, because if the programmer has done it before and is confident in a complex system, then the programmer is going to probably want to be like, wait, I'm capable of a fully custom on this complex process. If they're capable, they'll probably do it. Um, but if it's more of a, whether it's a newer engineer or new programmer, I should say, then they might be a little more hesitant to be like, well, wait, I don't have decades of experience, and maybe they're being mentored by somebody or what. Yeah, ooh, there's a lot of facets to that. Um, but yeah, I would say from my recommendation, at least when it comes to the combustion stuff, if we kind of hand over that actuator control, that flames detecting the flame, just let these approved systems kind of do what they do best. And then from a PLC, this is getting more and more popular. Our systems definitely interface with PLCs. And a common arrangement is I'm gonna broaden it in like the safety stuff as in the interlocks, the flame detection, and the actuator control, say for parallel positioning. Um, if you give all that to kind of what the LMV3, LMV5 is designed to do, let it do what it's best at. And then in terms of interfacing to a PLC, getting information, populating graphics, or just the burners, just a small process, a small part of a much bigger process. You could absolutely interface that with a PLC and put that on an HMI. That is getting very, very common in doing that. So yeah, so that's maybe the best way to answer your question is, I would say instead of PLC or a parallel positioning system, I think there's a coexist that, hey, let the LMV do what it does best and handling the safety aspects and approved um, and then, hey, the PLC, it can show information, it can control other processes. I would say that would be my recommendation.
Do you have any general examples that you can think of about where SCC products help to manufacture, or some projects in the recent past that you're like, hey, we really helped this person, or some positive customer experiences?
Yeah, yeah, yeah. So I'd say on an industrial process, I'll pick on or identify a certain industry, and that is the canning industry, the metal packaging, beverage cans, for you and I. And it is first of all, it's a very fascinating process of from sheet metal to a full beverage can. And that's kind of like the behind the scenes, kind of how it's made of our job, is pretty fascinating. So yeah, so a good appreciation there. But these canning processes, they go, they go 24/7. They run maybe 360 days a year. They do thousands of cans a minute. I mean, we're having, beverage cans all the time, right? Um, so we clearly need a lot of aluminum cans. So because the process is run so often and the burner needs to run so long, we'll say fuel savings, even if it's shavings, and some of the result has been at one application that I was at, it was around 4% was the fuel savings, after 8 to 10 weeks of operation, say before, because they had a fuel meter of before, and they can even do the amount of energy per can, which is a good neutralize constant. And they were able to improve their fuel efficiency by 4%. Now that 4% might not sound like much, but if your gas bill of running 24/7, 360 days a year, 4% could be quite a savings. And it's a fairly low return on investment.
Yeah, if your
What's-
if your gas bill is $1 million a month, 4% is over the whole year is a lot.
Exactly. So that's one of those where, yeah, it's a small thing. And that's a good example of, well, wait, small savings over a large scale. Oh, that's a really good candidate for parallel positioning. Um, Same thing I would say with big burners in general. Big burners, at least in a process standpoint, I'd say around 10 million BTU is a fairly large burner. That's a pretty large gas bill if you're running that quite a bit and above. That's where, uh, hey, if you're saving even a small percentage, even if it's running pretty good, like it runs ratio regulator, 10% excess air, but that at least with that electronic air fuel ratio parallel positioning, you could. Because you have these actuators and you could do whatever you want with them, you could just get a little more, get them more and more slim from an efficiency standpoint. Where a ratio regulator, the only two settings are the high fire setting and the low fire setting. Everything else it is what it is, right? And that's the other thing to note about this parallel positioning is these actuators, because these actuators rely on the air fuel ratio, any slop in the actuator means slop in the air fuel ratio, and slop in the air fuel ratio is a safety concern, right? So that's where kind of a magic number in terms of number of steps is 900 steps of resolution, which 90 degrees divided by the 900 steps, that's where you get that 10th of a degree control with these types of actuators. And that really tight control is, well, wait a second. That means when we get our air fuel ratio, we're getting it really tight because we're also getting closed loop feedback that the actuator is behaving properly, that we're really operating these actuators accurately. Because if we didn't do that, and let's say one actuator misbehaved and the control system didn't know it, that's a huge safety concern, right? Because then your air fuel ratio is going to go real far off. Which actually that brings in, I would say, another value point we haven't talked about. If temperature control, like down to the degree or down to kind of the fraction of a degree is important, then, these 900 steps resolution actuators, it's going to hone in that tighter control. Now, if you just need to dry it and you're just blasting, 300 degrees and if it moves a bit, no big deal. But there's some processes where that, hey, if you want a temperature really, really snug, whether it be, food for an appearance reason or heat treating for a metallurgy reason, something really tight, then parallel positioning is really good for that from a quality of product that it's making, to be able to control the temperature tightly.
The butterfly gas valves, does SCC make those?
Yes, great question. Quick clarification. So much of the products are Siemens, a lot of the electronic products, but the butterfly valve is made by our group.
Okay, so that butterfly valve that I think is definitely the most popular one in the industry for anything. I've seen anytime I look at a gas train, it's basically a SCC butterfly valve. It's a very great valve for a great price, but that one, it has a hole, or I guess it depends on how you can order the stem differently, but it allows a mechanical bolted connection to the stem, which allows SCC also sells a coupler that has a mechanical bolted connection. And then you have the actuator, which allows a mechanical positive connection. And those connections throughout don't rely on like a set screw slipping on a round shaft, but you get a direct connection that's close to the valve, and that allows you to have that resolution because while the actuator has all those steps of resolution, if you don't have that transmission as as close as possible to the valve, now you're going to lose it, and you get that loss of transmission at every point. So if you're using linkage, or I've seen people use parallel positioning but then like translate with linkage over to the valve for some reason, like you're losing resolution in all those points, and it ends up with being slop. But having the actuator mounted right to the butterfly valve in that case allows that very, very tight degrees of control. And that is especially important when the valve is closer to closed, because each degree has a greater impact of the pressure differential across the valve. Is that correct?
Correct. Yes. So as that butterfly valve starts to crack open, you will get an inrush of flow. So the tighter you can control that portion, then the tighter you can control the flow. And that's where that 900 degrees of resolution, or excuse me, 900 steps of resolution for that tenth of a degree, that's where that comes into helpful for things like turn down when you want to steadily control um, those low flows. And you're absolutely correct from a hysteresis standpoint. The coupler, the valve, at least in terms of a full, SCC valve actuator assembly, it is little to no hysteresis as compared to, say, a linkage. Oh yeah, if you push on that linkage versus pulling on that linkage, sometimes you can see it physically move. And that physically move is the difference between, wait, am I driving up or am I driving down? Um, and from an air fuel ratio standpoint, it is going to change in that case. So it's, but some people are, wait, that doesn't really matter so much. And that's perfectly fine then. But if it does matter, there is a path to, hey, we can correct that.
And that's also another important note. I think it's pretty standard in 2025, but sometimes there are people who have to make custom mount to valves and actuators because, hey, this actuator doesn't go to this valve, but SCC they have a general mount as well. If you are using an SCC, the butterfly valve, not with a SCC actuator, but they also have a specific mount where everything is done for you. You don't need any engineering or field drilling, and you can also order it as an entire assembly where you can get the valve, the coupler, the mount, and the actuator, and it's all solid and all engineered, and you have no hysteresis or very, very minimal to the point where you get a solid product and you're not relying on field engineering and field drilling and processing where, if you are converting an old process to an LMV5 or parallel positioning system, you can just change out the butterfly valve for the gas line, and now you can get an entire completed mount, and you're not trying to use an old butterfly valve and field mounting with and trying to make that connection and relying on your field engineers to make that connection. It's a full engineered assembly so that you get that reliability because, while you can math out on paper the savings you're going to get, it's only as good as the install. And if you're trying to hack together an install or you have actuators that don't go with butterfly valves and you're having to fab up everything, one, it takes longer and field labor is more expensive than ever, but two, you don't always get the best results precision wise. But SCC has a full package that you can just completely just have them assemble and you get it, quick install, and it's done. You wire it up and you're good to go.
Absolutely. Appreciate that.
Yeah, I mean, it's
Yeah.
big fan of, I've big fan of the LMV5. I can probably recite the manual. And we should also talk about the manual. The manual is online. You can download it, and SCC will also send you the book if you reach out to them. Everything is available on their website. Like we were talking about, scccombustion.com, and everything is there so that if you need information, you can download it and it's not locked behind a paywall or you got to reach out to a representative. Everything's there. All the air codes we were talking about are in the manual. The manual is very well written and it's a couple hundred pages, but that's good because there's some manuals out there that leave a lot out, or it's, hey, we have this manual and then here's the install manual, here's the field guide, and but all the information is in one spot for the LMV5, LMV3, which I think is great.
Yeah. And that was that manual was written by our group. So
Yeah.
that was, and it's standard across multiple products, the same format. So as you get familiar with SCC products, if you transition from one to the next, at least from a mental fatigue standpoint, it's very comparable.
Can we talk, unless you have any other, do you have any other examples about savings or about from my previous question about some retrofits?
I think the big one of efficiency, I think that's a big case. I think efficiency and also emissions. There's been some good success stories of emissions where, particularly, I know out in California has got really strict emissions requirements that are getting more challenging over time. A couple years ago, the the NOx level went even lower. So yeah, we've had some really good success there of um, our type of controls on a low NOx burner and being able for manufacturers in California to comply with um, those requirements. Yeah, to keep them running because I think there's penalties or you got to pay credits. Yeah, um, it's pretty tough if you don't meet those emissions. So we've helped some folks on that front. But there is one other question, and is more of connection to back to linkage was from the linkage from a safety standpoint. And I'm sure there's some cases and instances um, of a linkage coming loose and the possibility of wait, something either near misses or something could happen or something did happen from a loose linkage. Um, because I know there's in the environments that we deal with, there's heat, there's vibration, and the clamping force on that linkage. But you're relying a lot on those on that clamping force when you secure that linkage. I don't know. Can you speak to that? I'm sure that's a uh, depends on your experience kind of thing. Yeah, but what is
Yes.
your view of linkage, particularly from a safety standpoint?
So a lot of people don't realize that linkage, and when we talk about linkage, we're talking about spe- basically rods, threaded rods, and ball joints and solid rods. That's what we're talking about linkage, any mechanical connection. The entire linkage system, since it is the connection between, typically the most famous is the Honeywell mod motor. That motor, it can be any motor, and Siemens makes a great motor. Uh, but that motor that moves the air and fuel, all that mechanical connection is actually a safety system because it is linkage and it does connect to your air and gas. So that's part of your safety system. And I think a lot of people are undereducated about that because with linkage, and I do a lot of linkage training, with linkage, there's no, is it broke or is it good? Like if you allow your linkage to break or fall apart, you've already not done enough maintenance or preventative maintenance. And if there's any amount of play or any wear that's, I guess, greater than imaginary, I guess 10% outside of normal, you have to replace it and be proactive. So like ball joints and ball ends will wear out. And while they may not be bad, they're not great and you have to replace it. But when manufacturers or end users allow those ball joints and end connections to wear out so much that you lose control of the process, now it's still within range, but you're losing control. And depending on how large your burner is, especially at low fire, you will lose that great air fuel ratio. And with boilers, if your boiler sits at low fire a lot, you can sit up the boiler just because your butterfly valve is now 2 degrees open at low fire because of mechanical linkage. But with mechanical linkage, you're now also factoring in gravity. And when that linkage end does snap and fall apart because it's wore out, now gravity will pull on all those components. The arm falls down or in whatever is connected to the arm of your butterfly valve or air damper. And I've seen it a lot with boilers. Sometimes it can fall the correct way and your air damper falls wide open and now your boiler doesn't light off because you have 100% air on low fire and pilot. But I've also seen it fall 100% closed, and now it'll light low fire and pilot great, but now it modulates up to high fire. And the burner system, typically most famous is like a Honeywell 7800, that flame safeguard. It has no idea about the combustion process because all it does is there flame or is there not flame? And with linkage, there's no feedback of is while you have switches inside like a mod motor or any kind of motor to prove the high position, low position, you don't always have the position switches to actually prove is my air damper open and is my butterfly gas valve open? So I think a lot of people who or work on linkage don't understand how critical it is and how, even as you mentioned, hysteresis, a little bit of hysteresis, and that's basically essentially the motor starting to move. And if you watch a burner enough, you can see this, especially with a worn linkage. The motor will move, say, 5 degrees, but over 3 or 4 connection points going over to your butterfly valve, the valve hasn't even moved yet. So while you're calling for more heat in the oven, the temperature controller is opening the motor, so the motor is rotating, but the butterfly valve hasn't moved yet. So now your controller says, all right, well, we need to move more. So it opens another 5 degrees. But now your butterfly valve starts opening, and then it says, whoa, that's too much. So now it starts closing. But as you mentioned, whether you push or pull on the linkage, it changes the position. It's not going to be the same. So dragging it closed versus pushing it open, you're going to get two positions on your butterfly valve. And that switching position and modulating back and forth, especially, you are probably going to be modulating between zero. And by zero is it's not actually going to move the air damper or your butterfly gas valve. And now your mod motor is starting to have to move more, and you're going to get a very large curve for your temperature. And if you look at your PID and try to tune it, it's going to be not tunable because it's not repeatable for your temperature and your positioning. And that's where the direct couple of the parallel positioning system is, while the parallel positioning system doesn't actually prove that the gas butterfly valve is opening or at a certain position, you have essentially two connections, the top of the coupler and the bottom of the coupler, to the actuator. And that actuator has an internal positioning that if it's not at the position where it needs to be, the parallel positioning system is going to throw an error. So you're relying on two little tight connections of a direct connection that basically I've never seen with a Siemens coupler. I've never seen them like come apart. It's basically impossible for them to come apart under normal wear and tear. But with linkage, it's common all the time. Oh, we don't need to service our boiler or burner, whatever. And nobody notices it. And most mechanical things are, you don't service them until something's not working. And with an oven, it can just, oh yeah, those burners light. Yeah, they light. All of a sudden, one section of the burner, hey, burner 5 isn't lighting. You go to that section and, the air damper's flipped all the way open, and, the linkage rod is just hanging there. But also now going back to that, now you need to understand, hey, I'm going to get this all fixed up, but now you need to understand how to set up linkage. And linkage is, the adjustment of it is, as you're making concessions, and it's never going to be good. It is just good enough. And when you want that 4% savings on your $1 million fuel bill, you're never going to get that good enough to the point that it's going to be consistent. And there's just way more degrees of error, and you're now relying on that service person to be an expert in adjusting linkage and knowing how to adjust the travel and the speed and all that stuff. Whereas with a parallel positioning system, you just come in, type some numbers, and it's good to go for the life of the system. Yeah, you can adjust the numbers here and there, but if I type in 37 degrees, my gas actuator is going to go to 37 degrees, and it's always going to be at 37 degrees. And that is why parallel positioning systems and direct couple is very, very superior as far as reliability and ease of service over a linkage system that just has every single connection is another degree of failure that a lot of people don't realize. And you want always, in my view, you always want to reduce your degrees of failure to as low as possible. I've seen it done with, this could be a good segue. I've seen it done with gas trains. Gas trains have now I'm pretty young. I don't know when double block or double gas bodies got a thing, but every connection on a gas train is a point of leak. So if we can make our gas trains as short as possible and reduce the amount of connections, now we've reduced the amount of potential leaks. And if we cut our potential leaks in half, now we've reduced our amount of failure in half. And that's, I think, a lot of the benefits of parallel positioning systems are you reduce your amount of failure, and it's very repeatable to the point of what the screen says should be what the actuators are doing, where linkage, you're just kind of guessing.
No, that sums it up very nicely. And but I get that from a mechanical standpoint, the linkage, it is very visual. Where now direct coupled, it's also visual. You got valve indication positions. Um, but the crank arm, it is very visual. So I get that of, wait, the visual aspect, and from a comfort standpoint, wait, hey, if that service technician's been working with linkage, for decades, then it's like, wait, bridging to parallel positioning would have to learn something. But that's where, if ever that decision is made, there's benefits behind it, which we talked about. And we have resources, the training. I'd like to say that, particularly in my role, is, hey, I understand if somebody, wait, parallel positioning, they might be curious, but then wait, how do I really learn about this? And then it's like, wait, we as SCC, we've been in that position before. And that's what I'm here for, is we are to guide the customer, to try to help them. We'll get you comfortable with it. We got YouTube, we got phone calls, we got the support structure, we got in stock components. All these things are all intentional to build a certain narrative of, wait, hey, this is good for your business, and we're not going to leave you on an island. Yeah.
Yeah, there will be a learning curve, but
Yes.
one, there's already tons of companies, representatives out there that seen have seen LMV5s and LMV3s and other parallel positioning systems all the time. So it's not like they just rolled this out last year and we're pushing this product that's untested. It's very tested. It's been out. I don't know when the LMV5 came out.
Yeah, I want to say, I don't know. I want to say early 2000s, if I had to
Yeah,
guess.
it's
So
been
yeah,
2 decades,
yeah,
and uh, so while you may not know somebody that knows the LMV5 or LMV3, there's probably somebody in your area, a company that has somebody. But to have somebody learn it, especially if somebody is younger and they're used to computers and understand kind of how menus are set up, if you can't visualize the menu system of a parallel positioning, and I've seen older people kind of get not, they just didn't grow up around computers and they don't understand menu structures. But once you understand menu structures, it, it can get very easy to find things. If you don't remember, there's always the manual that you can open and look, and there's all, troubleshooting guides and everything in there. But there will be a learning curve. But, if you're getting 4% savings, take a little chunk of that savings and invest it into people and invest it into training. And yes, you may get a little bit of downtime here and there, but you're making a long-term investment versus holding on to old technology and relying on the way we've always done it versus adopting technology that's been out for decades and just trying to train people and say, hey, we're going to go to a full air code system instead of, I don't know, poke around and change components till something works. And,
yeah,
trying to troubleshoot old school relay logic is one of the hardest things, especially with no wiring diagram. And if you can just, hey, here's the screen, here's our little air code, let's go to the air code. Not that the air code is going to always tell you exactly what's wrong, but it gives you a general direction to go. And it says, hey, this is the issue. But, with the LV5, the low gas pressure air code, hey, low gas pressure. All right, let's go over there. Oh, yeah, we left the gas off during our shutdown. All right, great. Open it up. And that saves you a service call. And, that service call plus time is over $1,000. So, there's all kinds of savings, but it's getting comfortable with a new process is going to be just the first step, but it's well worth it just in the long term for the manufacturing reliability and embracing technology. And even though I would say it's not even new technology anymore, it's just getting with the times.
Um, yes, very much so. You know what? I'll even throw because the remote display are very handheld focused. You can almost throw video games. It is like the video game version of a burner. You push a button and which is really cool. That the technology exists to be able to do that, even though it's not all that new.
So I want to talk about the gas valves.
Yeah.
What are the benefits of, and I don't know, maybe you can talk, you're a little bit older than me. When did double gas valves, because it seemed to be like gas trains were 10 foot long, and now I'm seeing gas valves or gas trains are like all done in 3 feet, and double valves have become very popular. So it's going to be two actuators in one valve body assembly. So you're going to get your double block, but it only has one valve body. When did that become popular? And I would say the Siemens setup, like those, I see them all the time on pictures, and I see people using them all the time. So it's a very, very popular setup. What are the benefits of that setup, especially in a production type environment where space may not be available?
Yes. Yeah. Yeah. So the term, well, I don't think I'm that much older than you. I think we're pretty close. We're almost the same age. So I can't. I'm not a good historian on this
I mean,
topic.
I'm only 32.
I'm 38. So okay, all right. We're listening to the same music and stuff like
Yeah.
that. But yeah, but like the term like double block and bleed being an IRI term, being really common. Um, and yeah, and kind of the transition from, to say large single valves to a double valve. Yes, absolutely. From a leak standpoint, that's been really good from an installation. Um, so there's the less leak points and less connection points, to make it easier to install. And I would say on the SCC shutoff valves, one of the things that's kind of unique about our valves compared to the industry, is a lot of the industry uses solenoid, so being a coil, and using magnet and opening and closing the valve, that way, where the SCC valve actually use electrohydraulic. So there is kind of a hydraulic pump in there. And one of the top benefits is actually efficiency. So a hydraulic pump is a lot more efficient. I think it's about 10 VA, 10 watts of an SCC safety shutoff valve, where a solenoid, especially a large one, that could get up. I've looked at this at some point, but 60, even 80 watts. So there's quite a percentage of, from an efficiency standpoint. Now I realize that the electric bill, this is like a big light bulb versus a small light bulb. So from the business case for that is a little bit harder, from a dollars and cents. But in terms of concept of like, hey, you know what, you want to find some electrical savings, then that's a easy one to go. But back to the electrohydraulic, I would say it is very much fail safe, and the reason why is because actually at the bottom of the valve, there's almost like you can almost see there's like a bump in the bottom of the valves, and there's a really strong stiff spring in there, and that is always trying to close the valve. So no matter what happens, that spring is doing everything that it can to try to close the valve. And then it's the hydraulics that overcome the spring and then overcome the incoming pressure, because the incoming pressure is on the spring side, right, of the valve. So even at higher pressures, higher gas pressures, it actually helps close the valve rather than higher pressure starting to open the valve, which would be a problem. So then it's as the actuator, the shutoff valve actuator, electrohydraulic, as it kind of pushes down on the stem, it overcomes that spring, and then here comes the flow. So that way, in terms of being fail safe, if anything were to happen, of well, wait, something gets hit or the actuator's not working properly because all the electronics are all in the opening of the valve, where the closing of the valve is static. Always trying from a safety standpoint. Um, so yeah, I'd say that's kind of the big differentiator. Is yeah, that double valve for less leak points for a smaller fuel train, as well as that electrohydraulic. And the other thing that we could do with electrohydraulic is we could do a combination shut-off valve and regulator, which is very popular. So that way, in one device, we'll say in one double valve, you could have your two shut-off valve requirement as well as a regulator, all in that double valve body. And if it has a regulator, it has a gas sensing line. And if you can use it as a ratio regulator, like we talked about earlier, where air and fuel and the air and fuel kind of stay together. It's got an air impulse line as well as a gas impulse line. That just makes for a real snug, efficient fuel train of consolidating, say, ratio regulator or reducing regulator, and safety shutoff valve. The technology is there to do it in one device. So yeah, I'd say that's the flyby version.
The SKP 25, that's the valve he's talking about. Very, very popular.
Yes.
Do you know what kind of oil is inside the valve?
Ooh, I
I
don't.
just asked for my own because I took apart one on and I made a video on my YouTube channel, and it's a clear, very lightweight, very light viscous or low viscosity oil, kind of like mineral oil. I'm not an oils expert, but it
Okay.
was the first time I took one apart, and I was surprised at how the inside worked and how the pump was manufactured and like the bypass. But it was very intriguing. If you want to go check it out on my YouTube channel, it's there. But
Oh, nice.
I didn't know if you knew what kind of oil was inside.
I did not. I could inform you. I need help on that one.
All right. Yeah, that was just for me. But how does somebody how do you size a gas strain? How do you know what size valve bodies you need?
Good question. Okay. Well, first, is it, we'll say a traditional safety shutoff valve or a combination of a ratio regulator? Because the philosophy definitely changes between the two. What would you say?
We'll just start with the traditional.
Traditional. Okay. So traditional shutoff valve, you're going to want to minimize the pressure drop, right? There's the rule of thumb of, say, 10 or 15% of the required gas pressure at the burner. So if you just put simple numbers to it, let's say 10 inches of gas is required at the burner, 15% would be 1.5 inches of pressure drop across the double valve. That's pretty conservative. You can maybe get into the 20. You can get that a little bit higher. Which actually the point of is the higher the pressure drop goes across the shutoff valve, what the consequence of that is, let's just assume there's a control valve downstream of it, right? So there's a shutoff valve, butterfly valve, and then the burner that, say, requires 10 inches. So let's say we take 5 inches of pressure drop across the shutoff valve, right? So if it's so that way you would need 15 inches upstream, and you probably need a little bit more for pressure drop, but I'm making things easy numbers. 15 inches upstream of the shutoff valve, 5 inches of pressure drop, and then you need your 10, and that's where you get your 10 inches at the burner. Where if your pressure drop is too high, what happens is as you go down to low fire, the pressure drop of the double valves essentially goes away, right? So that means that the pressure downstream of the shutoff valve is starting to increase as the flow starts to decrease, which just puts a little bit more stress, I would say, on the control valve, because the control valve at low fire, um, if it has to control, say, 15 inches versus 11.5, the 15% rule, right? That's a little bit different. So the higher the pressure on the control valve, the harder for that butterfly valve, control valve, to control at low fire. So that's really the big consequence. So could you get away with more of a pressure drop from a percentage standpoint? Absolutely. But the top consequence is, wait, as you turn down, the pressure drop of the shutoff valve goes away, your pressure increases, And if your control system can handle that repeatably, then you could take, more shutoff valve. You could take more drop across the shutoff valve, which is a smaller valve, and a smaller valve is more affordable. So yeah, so that's the traditional shutoff valve sizing. You agree with that? Any other nuggets that I missed on that one?
I would agree with that. I would also say, some people think bigger is better. What is the downside of an oversized butterfly valve?
On a traditional shutoff valve arrangement, there is no downside, other than cost. So let's say if 15% of the required gas pressure, in terms of pressure drop, if you're at 10% or 5%, there is no, I would say, control consequence. Now, you will have to use a bigger shutoff valve, which is bigger piping. Um, so there's no consequence on the traditional shutoff valve. Now, this very much bridges as soon as we introduce a regulator, the SKP25. Okay, now there are definitely consequences to under and oversizing, right? So
So,
let's talk about those.
so going back, maybe I'm not thinking about it correctly. As you oversize your control valve, I thought this was in any sense. So if you only needed a 1.5 inch control valve, and now you get a 3 inch, each degree of resolution is now that much more gas. So now high fire is only 15 degrees or 20 degrees, and so you have issues controlling the burner because low fire is 2 degrees, high fire is 20 degrees, and you don't have enough resolution in the valve. Whereas a properly sized control valve, high fire is 70 degrees and low fire is 10 degrees. Is that?
Absolutely. Okay, so my mindset was on shutoff valves only.
Yeah.
And so you were assuming that the shutoff
No,
valve pipe size is in the controls out. Then absolutely, that's the top consequence. Yeah,
yes. Yeah. So shutoff valves, if you oversize it, a traditional shutoff valves, oversizing it, you just get a way bigger initial cost. And a lot of people will oversize the gas train just because a lot of customers or end users are like, I don't know, we'll have this incoming gas pressure, or maybe we'll have this. So it's easier to oversize and then make adjustments than to undersize and be like, well, we don't have enough gas. Now we got to rip it all out and upsize it. So yeah, so I was talking about the butterfly control valve because I've seen gas trains get oversized and they'll line size it like 3 inch all the way through to the butterfly control valve, and now that control valve doesn't have the resolution. I don't know if they talk. Is it CV? Is CV a thing of butterfly valves? I don't know if
for sure.
that's a.
For sure. Yes. CV, the flow coefficient,
Yeah.
anything with a pressure drop can be spoken in CV. And absolutely, yeah, from a control valve wants pressure drop, where a shutoff valve, at least from a perfect system, you minimize pressure drop. So there is definitely a balance of, wait, too big of a pipe size is an oversized control valve. But that's where, at least in terms of our offerings, we do offer full, medium, and reduced port. So with a given pipe size, you can be, essentially one pipe size less or two pipe sizes less, essentially. So we can help with that. And that is very common that a control valve, you see pipe, a control valve, you neck down and then you neck back up. Particularly on airlines, because airlines pressure drop is costly. If you need a bigger blower, longer lines, that kind of thing, but you also want good control on the air valve. So yeah, you want a smaller, you want a properly sized air control valve, but air pressure is expensive because you have to pay for it in the blower, in electricity. So yeah, but yeah,
And
okay. So go ahead.
yeah, well, and what about the sizing of a SKP 25 gas
Okay.
train?
So the philosophy completely changes, right? So I like to let's talk about, let's say, a regular or just a standalone reducing regulator. Sizing a standard reducing regulator Particularly, there's the pipe size of it, and then there's the orifice of that regulator. So, so that orifice is really important in that reducing regulator, because if that orifice is too big, then the reducing regulator from high fire to low fire is going to only go from a portion open to then fully closed, just like the control valve, going from 5 degrees to 20 degrees. You have a short modulation range, where the more stroke you use, even in the regulator, the better it's going to control. So that's where, on the reducing regulator, the sizing of the orifice is really important. You want to use the smallest orifice you can without having too much pressure drop, because too much pressure drop cuts your top end capacity, right? So there is a sweet spot, right? Of you want to use all the stroke, every bit of the stroke that a regulator can do, but you don't want to limit it full open where you don't get your full capacity. So there's kind of that sweet spot. Now, if we take that concept of an orifice in a standard reducing regulator, and now we apply it to a safety shutoff valve, where the safety shutoff valve itself is the orifice. So very commonly, the shutoff valve, and let's just pick an example. Let's say a traditional just on-off shutoff valves, right, is 2-inch pipe size. Where now, if we're going to add an SKP 25 as, let's say, as a reducing regulator, then that's going to be typically 1 to 2 pipe sizes smaller than the 2-inch. So that's, now we're talking, 1.5 or 1.25 inches. And the reason why is because the smaller orifice of the shutoff valve itself uses more of the stroke of the SKP 25. And the more stroke of the SKP 25 that we use, the better it controls. So, so really and now the trade-off, or the teeter-totter, is between inlet pressure, and size of the valve. And just in general, if your inlet pressure is really high, then the ORIS valve, the valve body itself, has to get really small, because we want to take that pressure drop, in that case. And then same thing. If your inlet pressure is really low, let's say something in inches, then your shutoff valve is going to be, we didn't want to keep that pressure drop low. So the rule of thumb is to size the valve for 90% of the available pressure drop. So let's go back to, let's say 10 inches required at the burner, right? And let's say we got, 3 pounds. So 3 pounds, what is that? 25 times, about 80 inches-ish, right? So now it's 80 inches coming in and 10 inches required at the burner. Then technically the available pressure drop is 80 minus 10 is 70 inches. We want to size the double shutoff valve, or 2 singles, to take 90% of that 70. And you see how, 90% of 70, that's around a 60-inch pressure drop. A 60-inch pressure drop is a much smaller valve than, say, 15% or 1.5 inches. You see how the valve size changes significantly from using SKP 25 to not using SKP 25. Is that, I know that's a lot of words, for the podcast, but hey, that's, but you know what? Good news, before maybe you chime in, we got a program that does all that for you. It's just, we got a sheet for it. You type in your numbers, what are you looking for? Boom. And then it gives you the bill of material with engineering details. So
where can they find that?
I believe it's on our website. It is on our gas valves page. Or contact us. We'd be happy to give it. We'd be happy to give it to you. It's a tool.
So if you didn't understand a thing he said, that is fine. Yeah. It is the math. The math is the same, and it is constant as long as you understand. I think it's just you need to know your BTU input and your inlet pressure. Are those the two? What field measurements do we need?
We need 3 things. We need what flow we want, so BTU. What is our inlet pressure, also called plant pressure? What's the available pressure that you have? And then what is the
inlet pressure at your equipment, not to the building? like where your burner is going to be installed, what can you actually get there? Because I've seen people say, hey,
Okay.
we have 20 psi at the street, but at our actual burner is maybe different. So actually where your burner is going to be installed, that
Yes.
pressure, that's your inlet pressure.
That's your inlet pressure. And then the pressure required at the burner, which is usually something pretty small. So it's those three things, the flow, and then essentially the available pressure drop. That's really what we want, is how much pressure do we have to work with? How much pressure do we need at the burner? We subtract them, and then 90%. And then, what valve is closest to that 90%? Yep, which is generally, and at first, if you've never done it before, and especially if it's around, say, 3 psi-ish, it's going to be like, wait, this size of burner uses a 1-inch double shut-off valve? It's going to be like, wait, this doesn't seem right. But it is. It is. It is a smaller. It is definitely a smaller shuttle valve, especially in the higher pressures. If it's 5 psi or technically even up to 10 psi, where we want to take a lot of pressure drop across that valve has to get smaller. So we use all of that stroke. And then the other way around, which we didn't necessarily touch on it, was if it's oversized. So let's say if we have a whole bunch of pressure and our orifice of our shutoff valve is too big, then what happens is the shutoff valve is going to crack open and you're going to get a whole bunch of flow. And then high fire to low fire is going to be such a small stroke. And then it's a resolution problem, right? That it's like, wait, I have such a small stroke to work with, like we need to use a smaller valve so the shutoff valve opens more and we have much more of a stroke to control much better.
Yeah,
Yep.
that's if you don't understand, that's why SCC exists and also why they have their program on their website. I believe it's just an Excel document that you can download and got it's got a program in it. You can program inside Excel, and as you change it, it builds out a diagram and tells you what you need to order along with the model numbers. So it does everything for you. But I would say number one thing is don't rely on your customer to tell you what their gas pressure is unless they're ready to sign a sheet. If they say, hey, we have 10 psi, send them an email or a sheet that says, hey, we have 10 psi and I'm signing off on it. Otherwise, go out and measure it yourself because customers are mistaken all the time on what their actual inlet pressure is, and they may misunderstand. Oh, that's at the street. Oh, that's what the gas company told us. Oh, but this building in our plant that we're actually installing the burner has a regulator underground or something and only has 5 psi. Go measure it, especially if it's an existing burner system. Go measure it. It is well worth the time before you order a $15,000 gas train and find out that it's improperly sized. And now you either have to replace it or it's going to not work well for the life of the gas train, which is no good. So always make sure that those three variables that we talked about, but inlet gas pressure is key, and don't guess because guessing just ruins the whole process of correctly sizing the gas train.
Correct. And you can't necessarily get conservative of like, wait, I'll just use a bigger valve. Cause it's like, oh, wait, there's something on the other end of that wait, it's not going to control very well because it's a lot of pressure. So which sometimes it's like, wait, a bigger valve bigger is always better, where it's there's a bit of a cautionary tale there, um, to understand that.
Absolutely. Well, I think we've covered what we need to. We're coming up on 2 hours. But how do if you're an end user or if you are a uh contractor and you have somebody in the process, furnace, oven, or even boilers, you can reach out to SCC. But if you have a process, should they reach out to you? Should they just reach out through the website and then get connected to you, or?
Uh, they can reach out to me. We don't have that that big a office, so it's if it's not on the industrial side, I could certainly I'll get my colleagues. That's a very easy transfer to do. Yeah, my email is my name, sfogle at scccombustion.com. Fogle is spelled Fogle.
Yeah, that and in about a month, if you're going to AHR, I assume SCC will have a booth.
We will.
Yeah,
Yes.
so will you be there?
I'm going to be there. I'm taking the later. I'm taking the Wednesday. Because it's Monday, Tuesday, and then a Wednesday.
Yeah.
Yeah, my colleagues are handling Monday and Tuesday, and I'll be there on Wednesday. So it's the less busier times is what I got. But yeah, no, stop on by.
Stop on by, talk
We'd love to say
to
hello.
the experts at SCC, and they also have a ton of local companies that does SCC have like authorized? I don't think like official authorized representatives or more. I think it's more of, isn't it more of like kind of a loose agreement kind of thing? I don't know how that works.
Oh, so we don't have formal contracts.
Yeah.
We do have handshakes of representatives. We do have representatives throughout the country. And the posture, put it simply, is wait, or you meet a criteria to being representative? Is it good for both businesses? And it is a handshake. It is an integrity situation. That
Yeah.
that hey,
But
we prefer to do business that way, because if it's not good for either party, then wait, a contract is very binding and it's a legal situation where we prefer to be work based off our word and integrity.
yeah, that's one of the benefits of SCC and their products is you can get them from multiple companies and there's no territories and contracts and all that. And if there's probably somebody in your area, if you don't already know, that SCC can recommend, and hey, these people know the products and can help you and troubleshoot if you are an end user or contractor, because a lot of time mechanicals don't have the bandwidth to become experts in burners, but they pick up projects that are burner projects and may need to bring on another level of specialty, which a specialty contractor on the burner side is well worth the money to get the project right the first time. Is that any other thoughts?
Uh, no, that's all. And we're recording between Christmas and New Year's, so Merry Christmas, Happy New Year, Happy Holidays.